So the basic problem that this talk is about is that when you do interpretable machine learning, you can estimate some dictionary of interpretable features, or maybe you have a dictionary without estimating it, and you have directions in your latent space that correspond to these features, but you don't really know what to do with them. You have a latent space that has coordinates that do not have an intrinsic meaning. You have these features that do have intrinsic meaning, but you may have more features than you have dimensions of your latent space. You may have relations between these features. And so this talk is a way of basically paring down these features. So in particular, the way that we propose to pare them down is to select from among these feature gradients features that have gradients that are length 1 and are orthogonal with each other. So if you have a matrix whose columns are length 1 and orthogonal, that's called an isometry. That's why the method is called isometry pursuit. So our goal is basically to take in a wide matrix representing these arrows of different colors and select from among them this submatrix that's the canonical basis. The first thing we do is introduce a loss that measures whether we're doing a good job of this or not. This loss takes the singular values and rescales them so that singular values that are below 1 are penalized in some equivalent way with singular values that are above 1. So like 0.5 and 2 have the same loss. There's a couple other nice things about it. It depends on all the singular values in the matrix, and it's uniquely minimized by isometric submatrices, isometric matrices. To give you some more intuition on it, here's the rescaling function that we're applying to the singular values here with different values of this parameter c. And then here's a diagram of our isometric matrix that has loss 0 using this loss. So we would like to find the submatrix that has loss 0, if there is one. And this is a best subset selection problem. There's kind of two sort of off-the-shelf solutions for doing this type of thing. There's brute optimization, where you enumerate all the combinations of elements. This is, always find the global optimum, but it's slow. Then there are greedy methods, which might not find the global optimum, but are faster. So sort of a generic coordinate selection problem. The main methodological contribution we have, besides this overall framework, is this convexified estimating procedure. So you all are probably familiar with linear regression, like y equals x beta. So here we have y is this d by d identity matrix, where d is the dimension of our latent space, so like 2 in the example I've been showing you. And then our x is actually this renormalized x, where we've renormalized the arrows so that the arrows that are longest after normalization are the ones that are closest to length 1 before normalization. Then we plug that into this multitask basis pursuit objective here. You see that there's some grouping over the features. So we're using L1 norm across all of our different arrows so that we select arrows rather than just the x coordinate of a given vector. So while this last point here is kind of a heuristic, we think that the minimizer is within this retained set. So we get a fair amount of sparsity just by running this basis pursuit program, and then that should be sufficient to then do a brute force search. The other thing that we should note about this objective here is that it favors vectors which are orthogonal to each other. So we kind of have an intuition for why this is a good idea. Here are the arrows after we've normalized them. You see that the purple ones are now the longest. If we run this algorithm, we immediately get the right answer for this particular example. If we run greedy, some non-trivial fraction of the time, we get wrong answers, like these two arrows on the right here that are roughly orthogonal, but one of them has length less than 1. We can look at this more systematically. So in this case, we're studying the iris data set of flowers described by their like sepal width, petal length, and we're trying to select some subset of flowers that are kind of mutually complementary. So maybe we're like making a bouquet. We apply this algorithm to like these randomly chosen subsets of 75 flowers, and we see that we get quite a lot of sparsity just in this basis pursuit formulation. Like between 4, which is the theoretical minimum, and 7 flowers are selected. And 7 choose 4, we can do brute search on that, so we can compare sort of the optimum of brute after this convex procedure compared to greedy search, and this kind of 2-stage selection does better than greedy most of the time. There's more results in the paper on this. But one question you might have is why does greedy do better some of the time? And it looks like this is because of mismatch between the basis pursuit objective and our original singular value-based objective. If we do brute minimization on the basis pursuit objective, then the isometry pursuit objective gives us basically a superset containing the brute minimizer. So the main message you should have here is that if you're using greedy or brute algorithms for coordinate selection, or maybe also diversification, you should think about convex approaches, and please try out our isometry pursuit. Thank you very much. Look forward to taking questions.
So in terms of interpretations or explanations, have you found any, how do you use this isometry pursuit, and what are the implications when you actually use it?
So that's a very good question. So the way we came up with this method was basically to select parameterizations of data surfaces in chemical physics. So in that case, we were trying to select features of molecular geometry that were parameterizing the data surface. I think that there's also an application in latent spaces of transformer models. Like people will train sparse autoencoders of a given width, and those can be thought of as like features P like this. So you could potentially pare down your set of features if you wanted orthogonal features using a method like this.
I understand intuitively why we want orthogonal vectors, but I'm not sure I understand as much what makes normal vectors useful here.
That's also a very good question. So in some situations, like diversification, it might not be that important. Mm-hmm. For unsupervised learning, where you want sort of like a geometry retaining embedding, in that case, you want to have like lengths preserved by the learned coordinates. So in that case, you might want length 1.
All right, thank you for coming to my talk. This is about GAMformer, exploring in-context learning for generalized additive models. This is joint work with Julian Arber and Frank and David at Freiburg, and Harsher and Rich at MSR. So the goal of this work is proposing a new method for learning GAMs, generalized additive models, that you heard a lot about from Rich earlier. And the core idea is that we want to marry a recent advancement in tabular learning, TabPFN, from the Freiburg lab with the interpretability of generalized additive models. And I want to give a little bit of background on what TabPFN is, because this is the work we're building upon. In TabPFN, the authors train a transformer model on synthetic tabular data to do in-context classification. So the transformer is fed XY pairs of training features and labels together with the test samples X test, and the output is Y test, so the predictions on the test set. And so this is trained on many synthetic data sets, like millions of synthetic data sets, and just with backpropagation, minimizing the loss on the test set. And then given the new data set, you just feed it through a transformer and out come the predictions. So this really does in-context learning for classification in a single forward pass, which is pretty amazing. So this on many benchmarks beats things like CatBoost, XGBoost, or other deep learning models. And it's much, much faster in learning because the learning is just a single forward pass in a transformer. So this is amazing, but it's restricted to small data sets because of the quadratic nature of the attention. So this is usually applied only up to like 3,000 data points. It's very black box, and it's very slow to predict. If you get a new row in your data set, then you have to run the whole transformer, and so it's much slower to predict than, let's say, a gradient boosting model or a neural network. And so, paraphrasing our two panelists, friends don't let friends explain black box models, so we want a white box version of this. So here we maintain a similar transformer architecture with some slight modifications, and we feed the training data and training labels into the transformer, but instead of making predictions, we get out shape functions. So given a particular data set, the transformer will output shape functions that make good predictions on the test split out of this data set. So given a synthetic data set, we split it into training and test part, run the training part through a transformer. We get shape functions. We use the shape functions to make predictions on the test set, and then we measure the loss on the test set. And then we do backpropagation through the whole thing. And essentially, the transformer learns how to produce GAMs in a in-context fashion. That this works is maybe a little bit surprising, but also pretty interesting, I think. One of the things that this has in common with TAPFN is we never minimize the training set loss. We never try to minimize or never try to fit the training set. We look at the training set, and then we come up with a model that we think will generalize well. So we directly optimize the generalization performance of the model, not the training set performance. This allows us to not bake any kind of regularization into the model. We use discretization of the features and then produce shape functions in the discretized space, but we don't impose any smoothness or any prior on the shape functions. We just let the transformer produce any shape functions, and then through the pre-training or meta-training, it learns that it's good, for example, to produce smooth shape functions. So one modification I want to point out maybe is that unlike in TAPFN, this is works on any number of features because we use two attention mechanisms, one across features and one across samples. And so this is equivariant with respect to the permutation of features. Okay, here's just a kind of plot on some toy data sets that you might be familiar with. And we can see here the GAMformer compared to EBMs on these 2D data sets. And so here GAMformer is strictly additive. So it's the sum of two univariate functions, but you can see the output is quite smooth, and on these toy data sets at least is quite accurate, at least as accurate as EBM. We also did a wider study on the OpenML CC18 data set, and this is a subset of this benchmark data set that contains at most 2,000 samples. Here's the critical difference diagram comparing TAPFN, EBM, GAMformers, and XGBoost. The models with the star here are models that have pairwise interactions. EBMs model the full pairwise interaction space. GAMformer, actually, we just pre-process the input to contain the product of the top features. So it doesn't model the whole interaction space, but you can see that essentially, TAPFN is better than the rest, but the GAMformer's interactions are as good as EBM with interactions, beats XGBoost, and GAMformer without interactions is nearly as good as XGBoost. Here's some examples of shape functions. These are actually it's the same data set that Rich showed earlier, and so for example, in blue is EBM and in red is GAMformer. You can see they're somewhat similar and somewhat different. Rich was very happy that we found the data imputation effect that he mentioned earlier. I think my time is up. And so thank you for your attention. Code is online. The trained model is online. The code for training the model is online. And my team is here in Barcelona.
Can you elaborate a little bit about the discretization step and like what gets lost in there?
Sure. So it's quantile binning. And so in this work, we only use 64 bins because the data sets are pretty small. We can also use, we trained the model with 512 bins. It's about as good on these small data sets. My assumption is that with 512 bins, you're not losing anything because that's what state-of-the-art tree-based models use. And so that's one of the motivations is we think we can do basically a sort of non-parametric version of the shape functions by using enough bins.
I'm curious about the training process. What sort of synthetic data sets do you use? How do you choose them to make sure they like reflect real-world data in some meaningful way?
That's a very good question. So we essentially use the prior that was used in TabPFN, and we know it's good because TabPFN works really well. What they're doing is essentially drawing random neural networks and then drawing random nodes from the neural network. And this gives you pretty complex correlation structure. And we also throw in some discretization and some missing values. But essentially, it's you do a random neural network, you feed noise into the random neural network, and then you pick up some nodes. Okay. And you call some of them features and some of them targets.
Interesting. And just generally speaking, what's the like computational cost of doing pre-training? Like how long are you training for?
Okay. I don't know off the top of my head, but it's substantially longer in TabPFN. This is I think something like 2 or 3 weeks on an A100.
Okay. Interesting. Thank you.
But then learning is for a particular data set is extremely fast because it's a single forward pass.
Sure. Yeah. Thanks.
I understand that you have a different attention mechanism, that you have both rows and columns, and it's different than TabPFN. If you would use the original TabPFN, but only move to GAMs instead of their original scheme, do you have a sense of what amount of loss do you get on different things? So to what extent does having GAM kind of reduce our space and give us errors? Or?
Yeah. I mean, we did that. That was the first thing we did. This is basically the structure they use in TabPFN v2. The problem is that you then need to train much longer because you need to kind of train everything separately for each feature because you don't have the feature permutation variance. So your model needs to be way bigger, and the architecture needs to be really weird, kind of, because you need to learn the shape functions either for each feature individually or. Okay.
Then I believe you, but then so do you have a sense of the V2, like a sense of how much we're losing, or are we losing it because we had claims in the morning, right, that there's almost no loss? So in that sense, this is another different view on this question. So do you have any?
I think there will be some losses on the benchmark data sets we're using. I think the question that I was discussing with Cynthia earlier is like, does that mean that our data sets are not as noisy as other real-world data sets? So I think there's data sets on which the complexity helps. There's something like there's a parity data set in there. There's like a 5-bit parity, noisy 5-bit parity in the data set. Okay. The EBM will not be as good on a 5-bit parity than a full model.
Okay. Thank you very much.
Thank you.
So thank you very much. First of all, I would like to thank the organizers for giving us the opportunity of presenting our work here. And I would like to acknowledge my co-authors, Sonia Moritz, and also Professor Julia Vogt from the Medical Data Science Group at ETH Zurich. So to get started, today we're going to be basing ourselves on concept-based methods. Concepts are, in concept-based data sets, what we have is the input and the supervised label, as in any other supervised training data set, but on top of that, we also have concept annotations. These are extra features that represent some human understandable concepts or attributes that are present in our input data. These kind of data sets are usually used in concept bottleneck models, and they need to be annotated manually, which is time-consuming and make them very scarce. For that reason, we wanted to see if we could actually use this concept knowledge that we already have and exploit it by incorporating it in other pre-existing methods. So the first method that we're going to be dealing with today is conditional diffusion models. In diffusion, what we do is that first we noise an input image, and then we learn how to reverse this process. And in conditional diffusion, we do so by also guiding our generations with the label information that we have. The second type of methods that we are going to be working with today are prototypical part networks. So in these kind of models, the model is able to first find prototypical parts from the training set and then make the classification according to the similarity between the latent patches of our training images and then these prototypes that we are also learning alongside. In the original work, Protopinet, the prototypes belong to each class, as they are separate for each of the classes, but then there is an extension to this work, which is Protopools, in which the prototypes can be shared across concepts, across classes. So we modified both of these methods. How we did so? So we wanted to incorporate concept information, and let's get started with concept-guided diffusion. Here, what we did is that we modified the traditional diffusion pipeline, and instead of conditioning on the label, which is what the conditional diffusion model does, we were able to learn a concept embedding in which we incorporated this concept information to finally obtain some generated images that incorporate this knowledge. In the second type of models, what we did is that the framework usually is used for multi-class prediction, and we basically converted it into a multi-binary label framework in which we trained the individual concepts and we treated them as the labels. So the prototypes retrieved were usually patches that corresponded to this concept of interest. This enabled us to have interpretable concept prediction, but on top of that, by calculating the similarities between latent patches of our training or even test dataset to the prototypes, we were able to obtain a concept prototype dataset. So what did we obtain with this? These are a few generations that we managed to obtain with our concept-guided conditional diffusion method. Something interesting here is that we were not only able to guide the generations to contain the concept that we were interested on, but also to not contain certain concepts. So as you can see here, we have the different 4 possibilities for the concept black wing and white belly. And in some cases, we have images in which none of them are present, or both of them are present, or just one of them, but the other not. We can also extend this to a multiple number of concepts at the same time. If you had the generations for 3 concepts at the same time, very few of the training samples contain these 3 concepts, but you can see that the model is still able to capture the dynamics. Sometimes the white belly is not exactly in the belly, but the white part is in the wings. But in general, the model manages to capture the concept information and to embed it into the generations. For the second experiments in the concept-guided prototype networks, here you have first the results for the interpretable concept prediction task. We are comparing it with the Oracle, which is the black box concept predictor from the standard CVN method. And there is a slight drop in performance, but at least our concept prediction is now interpretable. It is also relevant to say that the results are a bit better in the AWA2 dataset, which is a bit more complex. As for the visual or the qualitative results that we obtained, here you can see for both Protopinet and Protopools, and for 3 different concepts, black wing, yellow wing, and white belly. First, you have the original image with a self-activation map superposed on top of it so that you can see which parts the model detected as relevant to make the concept prediction. So you see that in general, in Protopinet, the results are a bit better in Protopools, so the model is able to actually focus a bit better on the relevant parts of the image. And you have also next to it the different prototypes that we obtained. We have so for the actual positive classification, so the samples in which it was classified as to having a black wing or having a yellow wing, but also for the negative ones. So we can see which parts the model found relevant in the training dataset to classify an actual sample as not containing a certain concept. Moreover, you have here some samples from the concept prototype dataset that we aim to build. You have the original image, and then the yellow square is actually the crop that our model tells us to do to get different samples. So in general, the results, once again, are a bit better in the Protopinet model than in the Protopools. And it is also relevant to say that sometimes the concepts are highly correlated between themselves, so that's why sometimes instead of focusing just on the black wing, it will focus maybe on other black parts of the actual image. So to conclude, with this work, what we wanted to do, our main goal was to try and integrate the concept knowledge that we have, and that it's sometimes very hard to obtain, into pre-existing methods to see if we could somehow leverage and exploit a bit more their knowledge. And we managed to do so in two different ways. First, with concept-guided conditional diffusion, in which we obtain visual representations of these concepts that can be useful in some downstream tasks, and also with concept-guided prototype networks, in which our objective was double, first obtaining an interpretable concept prediction, and then this concept prototype dataset with relevant patches from the training dataset. I think that it would be interesting to explore which are downstream tasks of further applications of these proposed models, and also it would be interesting to see if this could be generalized to other types of methods to make the most out of the concept knowledge that we have. If you're interested in discussing further, we have our poster. You can come visit in the second session and discuss a bit more. Or you can have an access to the full paper if you are also interested in more of the details. And now I'm open to take your questions. Thank you very much.